You already have done the conceptual map for these 4 topics. Of course, I think that you might be a little bit confusing about this algebra of simplex method. Today, I'm going to explain it. And then next class on Wednesday, we shall do the tabular form, okay? It's not really that complicated, but it has some mathematics basis. And that's where it's sometimes quite easy to get lost. Now, last class, we did the setup of the geometric solution in order to have an algebraic option, okay? And if you remember, we bring this augmented form of the model, okay? Where we add slack variables, okay? Because we weren't able to solve it. Now, because we have, in this case, 3 equations and 5 variables, we decided to divide them to non-basic variables, okay? 2 of these equations became mainly non-basic variables, and we decided to make them equal 0. In the initialization, in the geometric interpretation, when we choose double 0, what we were doing is choosing this x1 and x2 equals 0. Okay, now the other 3, we don't know yet their values, so we can determine by doing x1 and x2 equals 0. So we take this augmented form, okay? We're gonna take it, and what we're gonna do is x1, all x1 equals 0, and all x2 equals 0. That was a condition we decided at the beginning. So we have now that x3 is gonna be equal to 4, x4 should be equal to 12, and x5 will become 18. Andre? Okay, so my initial BF solution will be x1, x2 equals 0, x3, x4, and x5. Now they're 4, 12, and 18. So my solution, my basic variables are this. Now let's move to our optimality test, okay? In the optimality test, what we did here is, because it was not optimal, we decided to move along the edge, remember? And here we did, we consider the values that we have for coefficients. Now, in this case, what we're gonna be doing, and pay attention to this because we're gonna repeat it 3 times. This is the first one. Whenever we have positive coefficients, okay? Positive coefficients is a clue to determine that we are not yet in the optimal solutions. My lines are terrible. Let me sit straight or see what can I do. Nah, I don't think I'm gonna be able to do straight lines. Okay, so positive coefficient, it's a clue determine that we're not yet at the optimal solutions. So this coefficient, it's positive. This coefficient, the 3 plus 3 and plus 5, they're positive. So we are not yet in the optimal solution. Why? Because if we increase x1 and x2, we can lead to an adjacent BF solution that it's better than the actual. Okay, so, and this is general. If we got positive coefficients, we are not yet in the optimal solutions. Okay, let's go now to iteration number 1, step 1. Which direction should we go? This step, it's quite similar to the geometric solution. Here we have for z equals 3x1, if we increase x1 1 unit, our rate of improvement will be z equals 3. And if we increase x2 1 unit, our rate of improvement would be z equals 5. Because 5 it's greater than 3, then we select to move through x2. When we did the graphic situation, the geometrical, we said that we would be moving this way through x2 because it will enhance our performance, remember? And it's exactly the same decision we're doing here. Now, at this point, because we're selecting x2 as the edge through which we're going to be moving, that means that x2 will not be anymore a non-basic variable. It will become the entering basic variable. That means x2 will be changing places either with x3, x4, or x5, okay? Which one we still don't know, but we're gonna be changing that x2 with some of the basic variables. It will become a basic variable. For step 2, if somebody has a question, raise your hand, okay?
I do.
Yes.
But it's more to confirm that I understood everything. So
It's okay.
okay, when you move to the edge of something, instead of having zero, like 0.00, you have 0.10. Is that what you mean?
Well, here I started at 00, okay? 0, this is the origin. No,
Uh-huh.
here in the initialization. Here's when we say we're starting at the origin. Now, we are right now at the origin. Where should we stop? Right now, we are at the origin, 0, 0. And
Mm-hmm.
we know because of this equation at this point, okay, we know that we can increase. Here, we can go all the way to 5 units, 1, 2, 3, 4, 5. And here we can go all the way to 3 units. 5 is more than 3, do you agree? Am I answering your question? That was a yes?
Perdón, es que se trabó mi compu, creo.
No.
Entonces como que se mezcló el audio un poco.
Okay, do you want to do again the question?
No, I was on the explanation that you were giving to my question.
Yes.
O sea, estaba diciendo que we're on x00
Yes.
and that we need to move the
We're
edge.
here.
Ajá.
It's not that we need to move, it's more that we know that we can enhance z if we move. Yes or no? Here,
Okay.
z it's equal 0. Now, can we move? Yes, because we got 3 and 5 and they're positive. So yes, we can go to a better z. Okay?
Okay. Yeah, see, thank you.
Okay. Now, let's go to step 2, determining where should we stop. Okay? Here is different. This step 2 is different from the geometric interpretation because we need a mathematical basis, okay? What we did here in step 2 is that we say that when we reach the constraint, the restriction boundary of 2x2 equal 12, we would stop. Okay, now, how can we translate this into a mathematical formula? And here what we're going to be using is what we call the minimum radio test, okay? This is how we're changing a geometric solution into a mathematical solution, okay, into an algebraic solution. Now, let me give you some background. So if we increase through x2, that means x2 will become my new basic variable, okay? We don't want to overpass the situation where we go away from the feasible region, okay? Now, bringing back our equation system, our system of equations, if you remember, we say before that x1 and x2 were 0, okay? Now, because x2 becomes an entering basic variable, now we only stay with the x1. if we do x1 equal 0, I'm missing here some information. No, it's correct. If I make x1 equal 0, okay, and so now I can bring these new values of my basic variables. Here, if this is 0, x3, it's equal to 4. x4, if this is adding, it will pass subtracting. x4 equal 12 minus 2x. Okay, 2x2. And here, x5 will become, x5 is going to be equal to 18 minus 2x2. Okay, now we're going to take this part of the equation, this box, I'm going to bring it over here. Okay, and what I want to determine is how far can I go in these x2 values without violating this condition. So what I'm going to do is take this part, okay, and make them equal, each of them equal or greater to 0, greater or equal to 0. So 4 is going to be 4 greater or equal to 0. 12 minus 2, okay, is going to be equal or greater to 0. And 18 minus 2x2 is going to be also greater or equal to 0. Okay, here at this point, my values of 2x2, there's no x2 here. We don't have any x2. This one stays exactly the same. There's nothing to do about it. But this 12, it's adding, I will pass it subtracting. Let me explain it a little bit farther here, okay? I'm going to explain it. I'm going to try to make it clearer than what I was explaining. So here we say, we have before equation 1, equation 2, equation 3, where we have x1, okay, and we got also here x1, 2x2 plus x3, here is plus x4 plus x5 plus 2x2, and this is equal to 4, 12, and 18, okay? So we say that x1, it's equal 0. x2 now becomes a basic variable, an entering basic variable, so we can only change x1 to 0. From this change, we can say that x3 is equal 4. x4 is going to be equal to 12 minus 2x2. And x5 will become 18 minus 2x2 also, okay? Now, we want to know how far can 2x2 go at this point. Okay, for x3 equal 4, well, here, there's no much to do over here. So we got 4 will stay. It's going to be greater or equal to x2 because there is no x2 here, okay? The next one, we got x4 equal 12 minus 2x2. So I'm going to be taking only this part and I'm going to say 12 minus 2x2 is greater or equal to 0. So minus 2x2 is going to be greater or equal to minus 12. So x2 is going to be equal or greater or equal, but we're moving the negative, so we're changing here signs because we're moving to divide a negative value. So we change the greater to less, okay? And this is going to be minus 12 divided by minus 2. At this point, minus divided by minus, it's equal to plus, okay? So we stay with 12 divided by 6. and 12 divided by 6, it's equal 6, okay? And the last line say x5 it's equal to 18 minus 2x2. So how far can this x2 can go? This will be 18 minus 2x2 less or equal to 0. So minus 2x2 greater or equal to minus 18. So x2, we change the sign because this negative passes dividing. So we have minus 18 divided by minus 2. And minus give us plus, and 18 divided by 2 give us 9. And that's exactly what I got here. x2 less or equal to 6 and x2 less or equal to 9. Now, here I'm going to be choosing always my minimum value, okay? In this case, it's 6. Why the minimum value? Okay, I'm going to apply here the 6 at this formula, okay? It says 12 minus 2 times 6 is greater or equal to 0. And that's true because 12 minus 12, that's 0. It's greater or equal to 0. Okay, so I'm not violating this situation. Now, can I apply that 6 over here? Yes. 18 minus 2 times 6, that will be greater or equal to 0. That's also correct because 18 minus 12, that's 6, and that's greater than 0. So we're not violating any condition. Okay, why cannot use a 9? For example, if I use 12 minus 2 times 9 greater or equal to 0, what I will have is 12 minus 18 greater or equal to 0, and 12 minus 18, it's equal to minus 6, greater or equal to 0, and this is nonsense. So here, my restriction is my minimum value. I cannot go above 6 in order to accomplish these conditions, okay? So this is what we call the minimum radio test, okay? Choosing here the minimum value, what I'm deciding by choosing this value is that x2 is going to be changing places with x4, okay? So now x4 will become my living basic variable. Remember, this was my entry. They're switching places, okay? x2 is changing position with x4, and that means also that I'm going to be working in step 3 with, I'm going to start working with equation number 2. And that's what I'm saying here, okay? Now that here is summarized. I'm saying here, because this x2, it's less or equal to 6, and x2, it's less or equal to 9, my minimum value, it's a 6. So because it's 6, it means that x4 becomes the living basic variable, okay? Now, let's go to step number 3. Here in step number 3, we're going to be applying what we call Gaussian eliminations. Let me explain you a little bit more. Okay, so my initial BF was this one, where we have x1 and x2 equal to 0, and we get the solution of 4, 12, and 18 here. Let me show you. Here it is, 4, 12, and 18. Okay, now what we're going to be doing is x1, sorry, x2, it's switching places with x4. So now x2 becomes a basic variable and x4 becomes a non-basic variable. And we know that x2, it's equal 6. We determined that with the minimum radio test, okay? We know also that x1 and x4, because they're non-basic variables, are equal to 0. And we still do not know what are the values for x3 and x5, but we can determine them in a little bit later. First, we got to do some change in our original augmented form, okay? We got to do, we need to change this pattern 0, 0, 1 from x4. We need now that pattern to have it here. Here it's 5, 0, 2, 2. Well, now we need this pattern in order to keep working. How do we do this? We apply what we call series of Gaussian eliminations, okay? And it's quite easy, don't worry, okay? So how do we start? We say here that we were going to start with equation number 2, exactly. So we begin with equation number 2, okay? And at the beginning, pay attention. This is where we're going to start. So at the beginning, what I need here is this 2 become 1 because I got here a 1. I need this pattern of my living basic variable. This pattern should now become the pattern of my new basic, of my entering basic variable. I need here a 0, 0, 1, 0. Okay, I start with equation number 2. Okay, now pay attention. With equation number 2, what I'm going to be doing is I take the equation 2x2 plus x4 equal 12. All I can do here is either multiply the equation or divide by some number in order to change 2x2 into x2. So I decide to divide the equation by 2. Okay, so 2x2 divided by 2 brings me x2. X4 divided by 2, that's 1/2 of x4. And 12 divided by 6, that's 12 divided by 2, that's 6. And that's exactly what I'm explaining here. I take equation 2, okay, I divide it by 2. In my new equation 2 apostrophe, that means that it's my new one, it's x2 plus 1/2 of x4 plus equals 6. Okay, now, I say before that at this point, I could only multiply or divide. Now, the rest of the equations, I cannot multiply or divide. What I can do is add or subtract. Let me explain you. Let's go with equation number 0, okay? So we say this is my new equation apostrophe. Regarding equation 0, we got z minus 3x1 minus 5x2 equal 0. And I need this 3 to become a 0, the one that I got over here. How can I do that? In order to change these equations, I can add or rest equation number 2 or equation number 2 apostrophe, okay? And I can do some changes to these ones, okay? So if I need a 5, what I have decided is I'm going to be using my new equation here. I'm going to multiply it by 5 first. So watch. I take my equation 2 apostrophe, that it's x2 plus 1/2 of x4 equals 6. I multiply this by 5, okay? And then I'm going to get 2 apostrophe multiplied by 5. That 5 means that I'm multiplying 2 apostrophe, okay? So I'm going to get 5x2 plus 5/2 of x4 equal 30. And now I can bring it over here. I can use that equation in order to or equation number 0. This was equal to 0. So I bring this 5x2, okay, we say that this was equation number 2, 2 apostrophe multiplied by 5, so it's 5x2 plus 5 halves of x4 equal 30. And I only need to add. Remember, I told you we can only subtract or add. I'm gonna add here. So 0 apostrophe now becomes z minus 3x1. These are eliminated, and that's what I'm looking for. I need a 0 here, so it becomes 0x2, but we don't write it. We got now 5 halves of x4 equal 30. And if you see, that's the equation that I have here.
Teacher, so like the goal of this is to eliminate x2.
Yes, I need it because I'm trying to reproduce this pattern over here. And if you see, if it says 0, is that because it's eliminated, okay?
Okay, that's why in equation number 2 you still have x2.
Yes, because I need the 1.
Okay, thank you.
Yes, this pattern, the 0, 0, 1, 0, should be reproduced here, 0, 0, 1, 0. And so far, we have done it with equation 2 and equation 0. Now, let's go over equation 1. If we watch equation 1, the pattern that we have here, it's already 0. There's no x2. So there's not too much to do about it. We can say here at this point that pattern of equation 1 apostrophe, it's exactly the same pattern of equation 1. So if you see x1 plus x3 equal 4, it's exactly what I got here, x1 plus x3 equal 4. So there's no change, okay? It's going to stay exactly the same. Okay, and now let's work equation number 3. In equation number 3, what we got is 3x1 plus 2x2 plus x5 equal 18, okay? My point is, how can I use either equation 2 or equation 2 apostrophe to eliminate this 2? Okay, so I got here a 2x2 from equation 2, so I can use the original equation. So I'm gonna be subtracting equation 2. So I'm gonna be doing minus 2x2 minus x4, okay, equal minus 12. I just add them at this point and it will be 3x1, this 2 go to 0, minus x4 plus x5 equal 18 minus 12 gives me 6. And this is exactly the equation that I got here. So this BF solution, because of this Gauss elimination, became this to my new iteration 1 BF solution, okay? And that's what I explained at this point. Just what I explained at the display below, it's exactly the same what we got here, okay? And we got our new, completely new system of equations, okay? And we got here 0, 0, 1, 0. That's what we were looking forward. Our new coefficients for x2, the new pattern, okay? Now, since x2 and x4 are equal to 0 because they are non-basic variables, we can say at this point that with x1 equals 0 and x4 equals 0, we make all x1 equals 0 or x4 equals 0, and then x3 equals 4, x2, we already knew it was 6, and x5 equals 6. So my solution will be for my BF, my new BF solution, will be 0, 6, 4. And if I value at z, it was going to give me 30. Okay, so z it's equal to 30. And this is going to be my iteration 1 BF solution. Okay, where we exchange 2 with 1. Okay, after doing step 3, remember, we go back to our optimality test. And here in the optimality test, and this is the second time I'm repeating you, positive coefficients is a clue to determining that we are not yet at the optimal solution. Okay, I'm gonna take this z objective formula, this one. Okay, and I'm gonna put the z on the left side, and this is gonna be 30, because this one, it's subtracting, now it's gonna be plus 3x1, and because this one, it's also subtracting, now it's subtracting, now it's gonna be 5x2. And this formula, it's exactly the one I got here. 30 plus 3x1 minus 5x2. We still have one positive coefficient, okay? So it's not yet the optimal solution. We need all coefficients of the variables that are in the formula to be negative, okay? So let's go to our step 1 again. Step 1, increasing the value of the non-basic variable is equivalent to moving up the edge. So in iteration number 1, we move through this edge, x2. In iteration number 2, what we're doing is we're moving through this edge, and that's x1, okay? The criterion of the choice is, for the equation that we have of the objective formula, if x1 increases 1 unit, the rate of improvement will be of 3. If x4 increases 1 unit, the rate of improvement, it's negative. So 3 is greater than minus 5 halves. And at this point, we select S1 as the edge that through which we're going to be moving, okay? So x1 now becomes the entering basic variable. That means x1 will be changing places either with x3, I don't think so, x2 because it just came in, but I'm gonna put it in x5. It cannot be x4 because x4 is already a not basic variable, okay? Now, determining where to stop, step 2, okay? Here we're gonna apply again the minimum radio test. So first, what we're gonna be doing is defining the values for x3, x2, and x5. Here we know that x4 is equal to 0. So we do all the x4s become 0, okay? So x3 is gonna be equal to, this x3 is gonna be equal to 4 minus x1, okay? x2 equals 6, and x5 will become equal 6 minus 3x1 from this 3, okay? We're gonna take this right part. Let me go over here, okay? So at this point, we put this in zeros and we become 2, x3 equal 4 minus x1, x2 equals 6, and x5. Now, because here's no x1, there's not much we can do about it. It's gonna stay exactly the same. We're gonna touch this one, okay? But the other two, we got minus 4x1, it's greater than 0. We want to know how far can we move now in x1. And my second option is 6 minus 3x1 greater or equal to 0. So minus x1 is going to be greater or equal to minus 4, sorry. So x1 is going to be greater or equal to,
Teacher, but wouldn't the sign change? Because you're
yes,
dividing a negative number.
yes, you're correct. Yes, I was going to be doing that at this moment. Okay, so we changed the sign, okay, and it stays like 4. Okay, that's what you were saying, no?
Yes.
Okay, what I was gonna say is we got this, and here we got -1. This -1 is dividing, so we change the sign and becomes -4 divided by -1. Okay, so minus and minus gives me the plus, and 4 divided by 1, it's equal to 4. So x1 here is less or equal to 4. Now, nice observation. Thank you. Now, here, minus 3x1 less, greater or equal to -6. So now we're going to have x1, because we're moving this negative to the other side that it's dividing. We change also the sign, and we got -6 divided by -3. Minus and minus becomes positive, and 6 divided by 3 give us 2. Okay, so between 4 and 2, the minimum value is 2. Can we apply 2? Yes, it accomplished. 6 minus 2 greater or equal to 0. 6 minus 6 greater or equal to 0. Okay, if we apply it to this formula, does it accomplish? Yes. 4 minus 2 greater or equal to 0? Yes, because 4 minus 2 give us 2, and 2 is greater than 0. Can we use 4? No, we cannot use 4. Just on this one, if we apply the 4, 6 minus 3 times 4 greater or equal to 0, this will give me 6 minus 12, and this is -6 greater or equal to 0, and this is nonsense. We cannot use this one. So my minimum value that I can apply is 2. And this means that x1, by entering basic value, will be changing places now with x5. So this becomes my living basic variable. And I'm going to start working step 3 with equation number 3. Okay, the Gaussian eliminations. Now, before we do some Gaussian eliminations, let's come over here. And this is exactly what I say. This is the minimum value. So x5 becomes the living basic variable. Okay, now my solution at this point, my iteration 1 BF solution was this one. Okay, now if you see what happened here is now that this was my leaving and this was my entry. So now I got in iteration number 2, the x5, it's now a non-basic variable, and x1 became a basic variable. Okay, x1 has replaced x5. Okay, and now my system of equations for the new basic variable show in bold type will be these ones. The ones that are in bold means that are the basic variables. That's how we distinguish. Okay, now because we exchange x1 with x5, that means that the pattern of coefficients that we got here, now we want them for x1. We're going to be changing this pattern now through x1, and this is going to be through also through Gaussian's eliminations. Okay, so we're going to be doing exactly what we did in step 3, iteration number 2. Here's something wrong. This is iteration number 2. Let me change this. This is iteration number 2. Okay. It's saving. Okay, so iteration number 2, step 3, solving the BF. Okay, so remember that I said here that we were going to start with equation number 3 because we changed we exchange x2 with x5. So we're gonna do first equation number 3. Let's go over here and see how do we work this. Okay. So we have equation number 3, 3 apostrophe. Okay, it's 3x1 minus x4 plus x5 equals 6. If you remember, what I told you before is that we can only multiply or divide. So if we want this 3 become 1, we're going to divide everything. All this equation is going to be divided by 3. So 3x1 divided by 3 becomes x1 minus 1/3 of x4 plus 1/3 of x5 equal 2. And that's exactly what I got here. Okay? Now, let's go with the rest. I shall start with equation 0. I got here a 3. I also got here a nice 3. So I'm going to be using also the original 3 apostrophe, okay? Remember that what I told you, that we can only add and subtract here, okay? So I got 0 apostrophe z minus 3x1 plus let me put here, plus 5 halves of x4 equal 30, okay? And I'm going to be subtracting, no, I'm going to be adding, because I already have here the negative value. I'm going to be adding 3 apostrophe. 3 apostrophe is 3x1 minus x4 plus x5 equals 6. Okay, so we got z. This becomes 0, and that's exactly what I want here, a 0, plus 5 halves minus 1. My common denominator will be 2 halves. Okay, so this becomes 3 halves. So now I got 3 halves of x4 plus x5 equal 36. Okay, and that's exactly what I got here. Okay. Here, I'm trying to erase. Okay, so that was for 0, and this becomes equation 0 double apostrophe. Okay, that means that it's for the second iteration. Okay, regarding equation 1, okay, we need this 1 that we got here. Okay, we don't put it. Now I need it as 0. Now I got here a 1, and I got here also a 1. So what I'm going to be doing, it's for equation 1 apostrophe x1 plus x3 equal 4. I'm going to be subtracting equation 3 double apostrophe. So it's going to be minus x1 plus 1/3 of x4 minus 1/3 of x5 equal minus 2. Okay, so these two are eliminated, and now I have x3 plus 1/3 of x4 minus 1/3 of x5 equal 2. And this equation 1 double apostrophe is the same I got here. Okay, nice. And the last one, here we don't have an x1. That means it's already 0. So we can say that my equation 2 double apostrophe, it's equal to my equation 2 apostrophe. So it's exactly the same, stays the same, okay? And now I got here the 0, 0, 0, 1 pattern through Gaussian's eliminations. Okay, so we got here our new system of equations, okay? And we got the new coefficients for x1, 0, 0, 0, 1, okay? And since x5 and x4 are now the new the non-basic variables, then we can do all this equal to 0, all this equal to 0, it would be this. So now x3, it's equal to 2, x2, it's equal to 6, we already knew that, and x1, it's equal to 2. So my iteration number 2 BF solution would be now my non-basic variables, x5 and x4 equal to 0, x3 equal to 2, x2 equal to 6, and x1 equal to 2. And this is correct because at this point, we say that when we did here, my minimum was for x1 was 2. So of course, here it should be also 2, okay? So we finish step 3 and we go back to our optimality test. And we're taking this equation. This equation, we're gonna transform it, okay? So it's gonna be now z equal 36, okay? The plus 32 now becomes, the plus 3/2 becomes minus 3/2 of x4. And what do we got? Oh, here we have also a plus, so it becomes x4, this is a 4, minus x5. Okay, and that's the equation that we got here as the new objective function. Now, because there are non-positive coefficients, that means this is the current solution. This is the optimal solution, okay? For the ABF, it's 26200. This is for x1, x2, x3, x4, and x5, okay? And that it's exactly the numbers that we have for that second iteration. If we apply this equation, those values over here, we can see that we exchange the 0 and the 0, and we just get the 36. But we can also apply it to our original performance equation that was 3x1 plus 5x2 equals 36. So now we got 3 times 2 plus 5 times 6 equal 36. And if you remember, when we did the graphical solution like this specifically, this point, its coordinates were 2, 6. That was x1, x2. And z, the value here, was of 36. That was our optimal solution. Okay, so at the end of the day, what we have done is the geometrical algorithm, we have changed it into an algebraic algorithm. Somebody has a question here?
I have one, but it's really quick.
No problem.
Can you show the, no me acuerdo cómo se llamaba, algo elimination process?
Oh, the Gaussian.
Ajá.
The Gauss-Jordan. That the
Okay.
name comes from Gauss-Jordan.
Okay.
Yes.
Ajá.
Okay, what do you want to see?
Well, so here in this example, we're changing x5 to x1, right?
The pattern, yes. This pattern of 0, 0, 0, 1. Whenever we do Gaussian's eliminations, we're doing that. Did somebody of you guys at high school, maybe some of you guys, they show you at mathematics the, how did they call, when you have 3 systems, of equations like this. Let's say 3x1 plus 2x2 plus 6x3 equal 4, and then 2x1 plus 1 plus x2 plus 4x3 equal 2. And then we have x1 plus 4x2 plus 3x3 equal -1. You were able to solve this either by 5 solutions. One was sustitución, otro era igualdad, remember? Sistema de ecuaciones. And
The teacher, igualdad, I think it was when they were two ecuaciones.
Well, you can apply it also for 3, but you're correct. You start with 2. The truth is that you start with 2, but then you go to 3, okay? And this could go to 4 and 5. Always remember, the number of variables must be equal to the number of equations, okay? And then there were 5, okay? And the 6th one was eliminaciones por Gauss-Jordan. It has also another name, I don't remember now. But it's exactly, these are the Gaussians. Maybe some of you saw that at high school, not necessarily, but for example, those who were in Tech Milenio, I know they saw this. I don't know if in another high schools. What was your experience? Kramer, eliminaciones de Kramer.
Yes.
Bueno, Kramer es una aplicación de eliminaciones gaussianas. ¿Sí o no se parece?
Sí.
¿De qué escuela eres, Eduardo?
Algebraic.
Well, there in that school, of course, they also saw it. Okay, so it's not brand new for you. It's I know it's an application of that. Okay. Now, after this, what we have done, let me open the file we worked with last class. And if you remember, we have a triangle at the beginning, this triangle. And what we just did was translating this geometrical solution that's still, let's say, like half graphical and half algebraic. Now we have a full algebraic solution, okay? Next class, we're gonna be working the tabular. That means it's quite easy. It's exactly as algebraic, but it's easier, okay? You're gonna see, it's quite easy. And now that means we can use this in a computer. Of course, I'm not going to show you how to bring this into a computer language because we're not studying engineering. Okay, we're going to leave that for the engineers. But I think it's quite important for you guys to understand what's going on with this simplex method.